Thank you. Welcome. Good morning to everyone. Today, 19th of August, we are having our 19th webinar. Coincident that we are both 19. And I would like to welcome you for this wonderful session today, the topic which is relevant for every professions. So I would like to just introduce about NFE, National Federation of Engineers for Electrical Safety, which is born in the month of March. We have been growing as one of the fastest society in India, over 600 members today. And we are going to have 8 different chapters in the country. Our vision is to make every electrical installation free of accident, such as electrocution and fire due to short circuit, and increasing the reliability of the electrical installation, thus contributing to the savings of lives and property and supporting sustainable development. The mission is we shall strive to achieve our vision through getting accredited for products and personal certification. We shall focus on electrical safety by design, manufacturing, installation and maintenance of electrical product, and installation by competent and qualified manpower using quality resources, including product, process and procedures. I'm very happy to say we have as a moderator is our president of NFE. We also have Dr. Apau, who is the General Secretary, also joined as a participant today. I would request, I urge people who are joining now, we have over 450 plus participants today. I am urging, requesting all those who are related to electrical, please to join NFE. You will see in the chat box, my colleague will be giving you the link. Within 2 minutes, less than 2 minutes, you can become a member and you will get a certificate online. You'll get payment receipt and welcome letter from President and General Secretary. I would urge my colleagues who are joined, please do become a member today. At our upcoming event, we just completed the Bhubaneswar National Electrical Code, Make Our Nation Electrically Safe, with a punchline. We just completed our Bhubaneswar on the eastern side of India. We're going to have planning to have networking meeting and chapter launch in Mumbai, and followed by again National Electrical Code Conference seminar in Coimbatore on September 28th, and October 13th we are coming to Gurgaon, part of Haryana. And if you just want to run through various topics that we have covered, lightning protection, we covered part 1, and we spoke about CA, new regulations 2023. This all happened in the last June and July. And we also have a greater understanding with Association of Healthcare Provider, in short they call AHPI. So we will be coming certification courses for people who want to do audit in the hospital or healthcare segment. So that we have launched the partnership, and certification courses will begin soon. And we have completed Earth and Unearth system. And we also spoke about DISCOM and their responsibility, which was it was a panel discussion, very well understood. And again, CA regulation part 2. We also spoke about lightning protection part 2, and analysis of solidly earth system and resistance earth system. We covered in 5th of August this month. And today we have overcurrent protective devices. What does it mean? Ladies and gentlemen, thank you for joining today for our informative webinar on a crucial topic in the field of electrical engineering. Overcurrent protective devices. I'm very delighted to see such wonderful, diverse, enthusiastic audience from every corporate are attending today. We have from people from hotel industry, we have from data centers, we have from airports, from various diverse professions. They are joined today. So in today's rapidly evolving technologies landscape, ensuring the safety and efficiency of electrical system is paramount. Today, our distinguished speakers, Mr. Krish Theobald, has done extensive research in this field and ready to share his insight, case study, and practical recommendations. Once again, thank you for joining, and please feel free to ask questions. Please use Q&A box. Do not put your question in the chat box. My request is to every participant to put your questions only in Q&A, which will be attended by our moderator, Mr. Gopakumar. And let's make most of the learning opportunity and work towards safer and efficient electrical system together. Please join me in welcoming Krish Theobald and the moderator, Mr. Gopakumar, who will present on type of overcurrent protective devices. So myself, the host, Dominic, and I've been hosting all these webinars for you. And we have our president, Mr. Gopakumar. All of you must be very familiar with his name and his profile. He's very actively involved in NEC. He's actively involved in CPWD handbook, and is also the part of IEC, and lastly, National Building Code. So he's very familiar face. Now he has done over 18, almost 12 seminars since last 4 months, going across the country, talking about National Electrical Code of India. And we have our distinguished speaker today, Krish Theobald, who has been working on the ground with electrician. I'm again repeating, is working on the ground with electrician in India since 2017, learning from the basics of how to draw wire through conduit and how to chase walls. Very basic, very fundamental and electrical. How to draw wire through conduit. No, nobody even thought about it. So he has studied his BS 7671 in UK wiring regulations in great depth, achieving several qualifications in wiring regulations, inspections, testing, solar PV, battery storage, and electrical design. In December 2022, Krish stood among the top 2.16% of candidates taking the City and Guilds 2396, the highest level of electrical qualification in UK. Is a rare product that is available in India, and his qualification is just 21 years. He doesn't like me to tell his age, but however, I'm so proud that at a young age he achieved something very rare people achieve in their career. As a result of his proficiency with BS 761, he is highly skilled in LV electrical design to IEC 60364, harmonized national standard, including IS 732 and SP 30. Krish is the technical director at Chotego Plus Electrotech Private Limited, Mumbai. His own boutique electro-technical consultancy firm catering to heavy residential and commercial projects. He is currently a member of TMIET of the Institute of Engineers and Technology UK, and is also professionally registered as an engineering technicians with Engineering Council UK. Krish has appeared in several podcasts and shows in the UK, including Hit the Lights broadcast and FFIXS. How do you spell? I don't know, but that FX. With vast variety of on-ground electro-technical experience and expertise in wiring regulation, he is passionate about promoting culture of electrical safety in India. He, along with Mr. Gopakumar, has traveled length and breadth of the country talking about national electric code. Krish has been talking about wiring part of it. So this is about our speaker. Very interesting subject. I would now request our moderator, Mr. Gopakumar, to give opening remarks. Then Mr. Krish will take over from here. Over to Mr. Gopakumar.
Thank you. Thank you very much, Mr. Dominic. The activities, the awareness activities of NFE is keeping us engaged and the sleepless nights. Yesterday we had the program in Bhubaneswar. It was over by about 6:30. Then we took the flight at night and reached home. I don't know what time Krish reached. I reached about 2 a.m. in the morning. Then little bit sleep, and then again next day morning sitting in front of the computer. So anyway, these activities, of course, are becoming important now. The awareness is going up rapidly. The electrical inspectorates are supporting us very much. Yesterday, the chief electrical inspector of Orissa was with us almost the whole day, and they wanted to completely implement the NEC as mandatory in the state. So like this, a lot of changes are happening on the background. We are sure that our activities will start making the result very soon. So without much introduction, I would like to welcome Krish to start the program. Over to you, Mr. Krish. You have to share the screen.
Yep, just getting that done right now. Share screen.
Yesterday's program in Bhubaneswar, we made it in Silicon Institute of Technology. We had about 80 participants from all over Bhubaneswar. Yes, Krish, your screen is now visible. You can start.
It's visible, right?
Yes,
Yeah,
today's
please go ahead.
overcurrent protective device and how the OCPD such as MCB, MCCBs are selected based on the sizing of the wires and so on. Over to you, Krish. You can start.
Okay, hi. Good morning. Thank you for the introduction. So before we begin, I just want to say the term overcurrent protective device is generally refers to devices that protects electrical circuits from overcurrent, which is basically we're talking about short circuits and overloads and any faults of negligible impedance. So anyways, so let's just get started with this. So the presentation is broken down into 8 bits. We'll look at an introduction to OCPDs. So that's just an abbreviation for overcurrent protected devices. We look at some characteristics that are common amongst MCBs, MCCBs, and fuses, which are OCPD characteristics. These devices tend to be current limiting. We look at what exactly current limiting is, how they help, so on and so forth. Now, BIS is really stepping up their game. A lot of products are coming under mandatory certification. So we look at the status of ISI marking with regards to OCPDs. We look at coordinating OCPDs. So, often in electrical installation, just before or after the meter, we've got a cutout fuse, then maybe perhaps an MCCB. Then your distribution circuits are going to have MCBs or perhaps even other MCCBs or fuses. And your final circuits would have MCBs or RCBs. So how we coordinate these overcurrent protection devices. Then we'll achieve fault protection through OCPDs, which is your second layer of protection. So basic protection is when you have your insulation and enclosures. Fault protection is in failure of these situations, how you achieve automatic disconnection of supply, and how this ties in with protective earthing and protective equipotential bonding. We also delve slightly into protection against thermal effects of fault currents and protection against overload currents. And yeah. Okay, so the first section is going to be the introduction to OCPDs. So we'll first look at the different types of OCPDs that are in the market. What is an overcurrent, which is what an OCPD protects against. There are basically a couple type of overcurrent protection devices. We look at the 60898 Part 1 MCB. There's also the slightly more specialized 60947 Part 2 MCB. There is a 60947 Part 2 MCCB, molded case circuit breaker, and then there's a 60269 Part 2 fuses. This is a mistake. It should be 2. We're not looking at Part 3 here today. Okay, so The different types of OCPDs, like I said, we've got our miniature circuit breakers, our MCBs. We've also got molded case circuit breakers right here. And then we've got our fuses. So this is very commonly seen in domestic and commercial installation. This is seen more in commercial, large scale commercial and industrial. And these are seen in a variety of electrical installations. So what is an overcurrent and what does an OCPD protect against? See, there are three basic systems. There are three basic ideas. An overload, which is a fault-free scenario. There's nothing wrong in the circuit. It's just that there's excess current drawn by loads. For instance, you have a motor that is drawing, there is something wrong with the actual load and it is drawing more current. Or say you have a socket and you have a lot of loads connected, a lot of extension cords, so on and so forth. That's a fault-free scenario where there's excess current drawn by loads. Then you've got a short circuit between your line and neutral, which is in India we call it phase colloquially. Phase and neutral or phase to phase. And also in TN systems where your neutral is bonded to your earth, is connected to your earth through a negligible impedance at your transformer. Earth faults are going to have a negligible impedance, so this would essentially classify as an overcurrent. So these are earth faults of negligible impedance. These are three situations where OCPDs really step in. Overcurrents will eventually lead to fire because they lead to thermal stress. So you can see in this image here how a cable has been badly impacted by overcurrent. Okay, the first product is the humble MCB, the 60898 MCB. In India, we have a standard. It's ISIEC 60898 Part 1. That's for alternating current MCBs. These commonly protect final circuits, lighting circuits, socket circuits, perhaps water heaters, air conditioners, so on and so forth. These have fixed tripping characteristics. Well, that means that they cannot be altered by the installer. So we've got our type B, C, and D curve. As we know, B curve MCB strip between 3 to 5 times the rated current. C curve MCB strip between 5 to 10 times the rated current, and D curve MCB strip between 10 to 20 times the rated current. Sorry, yeah, that's right, 10 to 20 times the rated current. Fixed tripping characteristics, like I said, you only got B, C, and D options with the 60898. You can't suddenly say that, I want the breaker trip at times 8. So if it's a 10 amp breaker, you can't have a trip at, you have a 10 amp C curve breaker that would, in the maximum, the minimum fault current safely to require to trip would be 10 amps. So C curve, that would be times 10, which is 100 amps, but you can't suddenly say I wanted to trip at times 880 amps. It's fixed. The maximum voltage is 440 volts. That's line to line or phase to phase. That's what the 60898 Part 1 MCB is certified for. Then you've got the slightly more specialized MCB. These are 60947 Part 2 MCBs. These commonly protect specific loads, and here the manufacturer can define a tripping characteristic. So often you see a type K or a type Z, a type Z MCB. These are actually manufacturer defined. They're not in a standard, they just conform with the standard. Once again, these MCBs have fixed tripping characteristics. So they will trip at a defined multiple. We'll look at exactly what a type K and type Z are. They are more common amongst the other manufacturer-defined tripping characteristics. We'll have a look at this. Also, it's very common to have 60947 Part 2 MCBs that are also 60898 compliant. So, for instance, if you've got a single MCB, you'll have two certifications. That will be mentioned. Two product standards: 60898 Part 1 and 60947 Part 2. This could possibly be because it's a load with a regular characteristic, but the fault currents are higher. They're higher than what the 60898 is certified for. So then it would be dual certification. Also, remember 60947 Part 2 is a very broad standard. It covers MCBs, MPCBs, which are motor protection circuit breakers, MCCBs, which are molded case. It also does RCDs, RCBOs, MRCDs, some protected devices for DOL starter, and DC solar photovoltaic breakers. So it's a very broad standard that we've got here. Then we come to the very familiar 60947 Part 2 MCCBs, especially if you're working in the industrial and heavy commercial sector. Again, we've got an IS standard, ISI 60947 Part 2. These commonly protect distribution circuits, so they would protect the circuit that's supplying a distribution board, a sub-distribution board from a main distribution board. These commonly have adjustable tripping characteristics, so you can see you can set the current, thermal, and magnetic tripping here. I'll show you the different settings available ahead. There are two basic types of MCCBs that are available under the adjustable.
If you can make it a little bit slow, would be fine.
Okay, sure. Sounds good. I'll go a little slow, and then if that's good, just let me know when I'm at that speed.
Sure.
Sure. So these MCCBs commonly come in an adjustable type. There are also some fixed types. We'll look at that a little later. Commonly, we have thermal magnetic, which is similar to the MCB. There's a thermal part that works for overloads, and there is a magnetic part that works for short circuits or faults of negligible impedance. We've also got electronic release MCCBs. These allow us to set things like time delays. I'll show you some tripping characteristics of those. These 609.7 Part 2 MCCBs are certified for a maximum voltage of 1000 volts AC or 1500 volts DC. Then we've got the humble 61269 Part 2 fuse. Once again, there is a corresponding IS standard. It's IS IEC 60269 Part 2. These commonly protect distribution circuits again, so cables that go to sub-distribution boards from the main distribution board. These are often referred to as HRC, high rupturing capacity, or NH. It's a German term for that also means high rupturing capacity. These require a lower one-time capital investment as compared to MCCBs because purchasing a single fuse and a switch fuse disconnector is not as expensive as say an MCCB. However, if it blows, if it fuses, you have to replace it. That's something to keep in mind. The maximum voltage that these come in are 1000 volts AC. This is just for AC. They are obviously because 60269 applies to AC. And like I said, there's no flexibility compared to your molded case circuit breakers because you cannot set up adjustable tripping curves. There are no time delays possible. You cannot set any time delays on a specific fuse. You require a different fuse altogether. Now, when it comes to the characteristics of different overcurrent protective devices, I have broken it down. I give you three columns here: MCBs, MCCBs, and fuses. You look at the rated voltage, these obviously apply for all three. Rated currents obviously apply for all three. We've got utilization categories. I'll tell you, we'll get into what they are. These are only really given for MCBs to 60947 Part 2 and for MCCBs. And for the fuse, it's given for the active switch fuse disconnect. Number of poles obviously applicable for both MCB and MCCBs. And then again, for the fuse, it's only applicable to the switch fuse disconnect. We look at the conventional tripping and fusing currents and times. These are what currents cause MCCBs and fuses to blow or trip in overload conditions. For MCBs, these are again defined by the manufacturer. For MCCBs, these are set by the installer on those variable tripping characteristics. And for fuses, these are already defined by the manufacturer. You also got the cutoff and let-through current. This comes through the current limiting effect of these OCPDs. These are defined for all three. I square T, let-through energy characteristics. How much energy is let through before the device trips or fuses? These are obviously defined for all three. Energy classes are a simplified approach to let-through energy characteristics. These are only for 60898 Part 1 MCBs. Speed okay now?
Yes.
Then we
Yes.
have also come to sounds good. Thank you. Then we'll also come to selectivity categories, which are defined for which help us decide what OCPD trips first. There's a separate section on selectivity that we'll get into. These are only for MCBs to 60947 Part 2 and MCCBs. We also have the type of terminals. So how do the conductors connect to the protected device? How do the protected devices get into your wiring system? We'll look at that. And then there's a fuse system, which obviously only applies to the fuse. Right. Now, when we come to rated voltages, basically this is talking about the potential difference between the conductors in the circuits that the OCPDs protect. We've got a rated operational voltage, which is noted by UE. Basically, what it says is that this is the voltage that the circuit breaker, this is a voltage that corresponds to circuit that the circuit breaker may be installed in. And for a given voltage, there is a given short circuit breaking capacity. So for instance, just one moment. I've got an MCCB here with me, and it says for 220 to 240 volts, it has an ultimate breaking capacity of 35 kiloamps. For 380 to 415 volts, it has an ultimate breaking capacity of 25 kiloamps. And for 660 to 690 volts, it has a ultimate breaking capacity of 6 kiloamps. So that's how these are generally defined. There's also a rated insulation voltage, which is what is used by manufacturers for testing, for the dielectric test and the creepage test. Usually they test it's a reference voltage, so they test it 2 times the rated insulation voltage. Also remember that the rated insulation voltage will always be greater than the rated operational voltage. So And remember, these are usually given as line to line, so face to face voltages. You've also got the rated impulse withstand voltage. These are the voltages for which circuit breakers are tested to withstand operation without failure. This relates to surge currents and transients in the electrical installation. I won't go into too much detail about this, but basically it has to be rated to a value greater than the transients expected in the electrical installation. There are also specific requirements for this in IS 732 and NEC. When it comes to rated currents, all overcurrent detection devices have a rated current IN. This is similar to this rated operational voltage. It's the value for the current the overcurrent protection device can carry in uninterrupted duty, which means to constantly be able to carry it for uninterrupted operation throughout its lifespan. When it comes to 60947 Part 2 circuit breakers, CBR denotes circuit breakers, just so you know, you have a rated operational current IE, which is a maximum value of current that overcurrent protection devices can carry. And these are given for two duty cycles. The first is an 8-hour duty, and the second is an uninterrupted duty. See, generally, these 60947-2 circuit breakers, these are meant for competent people, persons to operate. These are either rated to run throughout the day or run only for under constant load for about 8 hours a day. So there are two rated current values that are given by the manufacturer. Then there is also the conventional free air current. So if the OCPD is installed in free air, it is allowed to carry. There's a certain test current that is used to see how much the temperature rises inside the internal components. Then there is also the enclosed thermal free thermal enclosed thermal current, which is a test current used for OCPDs inside enclosures. So, for instance, a switch view disconnector would be very commonly inside an enclosure, and so would an MCCB when it is through the rotary handle. Again, the if and usually these are given. So for MCCBs, you will get these values because MCCBs also correspond to 64947 Part 2. Once again, these values have to be greater than the or equal to the 8-hour duty value for the rated operational current, just because if a circuit breaker is intended to be installed inside an enclosure, you would obviously want it to be able to run at that particular load current for greater than its rated duty cycle. Again, if the device is meant for 24-hour duty, then it's a different story. Again, probably would be rated for that. Okay, so utilization categories are quite an interesting subject. It is basically the nature of current and nature of loads that the devices are switching. So when it comes to circuit breakers, these are, like I said, these are only given for 60947 Part 2 circuit breakers, and then for switch fuse disconnectors, and there are some other subjects as well. For generally speaking, these are for circuit breakers. These are given for AC22, which is if you refer to the 60947 series. This is basically a mixed resistive and inductive load with moderate overload. This is your everyday domestic situation and possibly some commercial situations. When it comes to the actual switch fuse disconnector or an isolator, there are four categories. There are switching, so you turn on and off under no load conditions. Frankly, that we see are rare. That is only the main switch on a domestic distribution board. You'll only turn it on and off under no load conditions. If you've got a resistive and moderate overload, that's AC21, that would come in there. Mixed resistive and inductive loads with moderate overload that come under AC22. And for AC23, it's a motor or highly inductive load. So when a protected device has a certain current rating, that is your IN, these are given for these utilization categories. So for instance, if you've got a device that is normally rated under AC20 for say 63 amps, but you're actually using it to switch motors and highly inductive loads, you cannot, and this is a different rating, say 10 amps. You have to use a 10 amp rating. So you have to choose the IN value. You can see these are provided on your actual protected device or switching device. You have to choose the IN value depending on the utilization category. That's quite important. For 60269, there are several utilization categories. We look at GM, which is general purposes, and there's also GG, which is general purposes, and there's GM for motor protection. There are various utilization categories, but for now, we'll just focus on these two because of the interest of time and making it general for everybody. When it comes to the number of poles, for circuit breakers and switch fuse disconnectors, that's what SFD denotes. There are basically, the basic way it works is that there is a the pole is a portion of a switching device associated exclusively with one electrically conductive path. So I think it really requires no introduction. That was just nomenclature. See, basically, you have the one pole circuit breaker, which is this. This is the one pole MCCB, by the way. Then you have your one pole plus neutral. This is a very commonly used term. What it means is that one pole is protected and the second pole is switching. However, if it is a switch fuse disconnector, one pole plus neutral often means that the two poles are going to be having a fuse holder, and the one may either be a switched or an unswitched link. Just one moment, please. Sure, what's happening? My apologies. Right.
Krish, you have to further slow down the speed a little bit.
Okay. Will do. Okay. So these one pole plus, like I said, so that you got one pole plus neutral. When you've got two pole devices, this means both poles are protected. So this would be a two pole breaker. Three poles would mean all three poles are protected. Three pole plus neutral is you've got three poles protected and the fourth pole is switching. Similar story like the one pole plus neutral. And the fourth pole is the four poles protected, including the neutral. See, the thing is, one pole plus neutral plus three pole plus neutral are commonly used terms. However, the correct terms as per the standards are two pole and three pole with, so for a two pole it would be it would be for a one pole plus neutral, the correct term would be two pole with one pole switched and one pole protected, or rather one pole protected and one pole switched or unswitched depending on the protected device. And for three pole plus neutral, it would be a four pole protected device with three poles protected and one pole switched or unswitched. So that's just for your reference. Right now, when it comes to the conventional tripping current, like I said, these are talking about overload situations. See, we all know that if we've got an MCB that's say rated for 16 amps or an MCCB for 16 amps, the moment the load becomes 16.1 amps, it's not going to immediately trip like this. This is not your instantaneous tripping we're talking about. This is talking about a slow tripping. This is under overload conditions. Generally speaking, these are given by the manufacturer. These will be given by the manufacturer for all devices, unless it is an adjustable MCCB, where then, depending on the overload release, the long time release, this is defined. But for say a fuse, for an MCB, and yeah, these are going to be defined. So for instance, for a HRC fuse, this is 1.6, which means that say it's a 63 ampere HRC fuse at so let's just simple example, 10 ampere HRC fuse at 60269 part 2 at 16 amps, it will trip in 1 hour. So that's how these are defined. If it's a 10 ampere MCB to 60898 part 1 at 14.5 amps, it will trip in 1 hour. These are talking about what currents the protected device will disconnect at in overload conditions. Yeah, same with MCCBs is set by the installer or manufacturer. Now, short circuit characteristics. This is rather interesting because very often these terms are thrown around by manufacturers. So let's have a look. ICU, which is very often the rated value, and these are given as ICN for MCBs to 60898. These are the ultimate short circuit breaking capacities. Frankly speaking, the OCPDs are only designed to break these once. If they break this value more than once, then you need inspection by the manufacturer or yourself under some detailed checklist. So for design, we use something called ICS, which is the in-service breaking capacity. These are all root mean square, by the way, values of current. What this is what value of short circuit can the OCPD disconnect constantly under design. For a fuse, obviously, once it blows, so it's not valid. And generally speaking, so the standards require this in-service breaking capacity to be at least 0.25 of the ICU, the alternating capacity. So I've got an MCCB here, and see, for instance, for 415 volts, the this happens to be that the ICU is the same as the ICS. So because it has to be greater than or equal to 0.25 ICU. So obviously ICS is equal to ICU is perfectly adequate. Now, um, the point is that certain devices, you will say that the value of ICS is significantly higher than the value of ICU. So I'm sorry, I will repeat that again. The value of ICS is, say, significantly lower than ICU. So maybe it is zero point 0.5 or 0.75. We need to take this into account, because if a manufacturer tells us that the short circuit rating, the short circuit breaking capacity is, say, 10 kiloamperes or say 35 kiloamperes, it may very well be that it's only designed to do 15 kiloamperes, or okay, let's restart. Which says 35 kiloamperes, it may very well be, see, 35 into 0.25. It may very well be that the device is only rated to interrupt 8.75 kiloamps under continuous service. So for design, the ICS value is important. Manufacturers will also give us an ICM and what's called an ICW. An ICM is, in case during a short circuit, in the first half cycle of the wave, the peak current is this. This is the peak current value. If the OCPD is, this is for a circuit breaker really. If the circuit is completed during that time, the OCPD has to handle that peak current value. This is what the ICM value is. This is really only for manufacturer. I said for designer, these values are applicable. For manufacturer, these values are applicable. There is the ICW, which is technically applicable for both. What this means is that if you have a breaker that is going to have a time delay in it, which will wait to trip after a certain short circuit is detected, the components of the breaker have to be designed to withstand that value, which is what this ICW is. These are given for certain times. So generally 0.05 seconds, 0.1 second, 0.25 seconds, 0.5 seconds, and 1 second. So this is to do with selectivity. We'll get into this a little later. The speed is okay now.
Yes.
Okay. Now, when it comes to overcurrent release characteristics, I'm sure those working in the heavy commercial sector and the industrial sector have seen these dials on our MCCBs. So these are basically the time current conditions which cause an overcurrent protection device to interrupt the flow of current. For an MCB, these are fixed B, C, and D. And this is to 60898. And for 609 for 7 part 2 MCBs, these are manufacturer defined. Commonly you see K and Z. I'll show you the tripping curves in the next slide. For a fixed MCCB, it will be certain overload current and a multiple of ions, say 8 ions. So for a 40 ampere, that could be 320 amps would be the tripping current, instantaneous. Then for an MCCB adjustable, you have got something called L, S, and I. You also have G and all that, but we'll only look at L, S, and I. L is the long time, which is to prevent tripping when there are starting currents or high or if there are inductive loads that draws a great amount of current in the beginning. S is a short time tripping, which is to define if there is a breaker that has to wait to trip, how much time will it wait, what current will it wait for. And I is the instantaneous current, which is if there's a certain amount of current, the breaker will trip without waiting. For a fuse, this is as per the normal current and the utilization category. So if it's a GM fuse to 60269, 10 amps, a certain fuse system, it'll have a certain defined tripping curve as per 60269. So there's nothing to change there. So for MCBs, you've got your Z, B, C, K, and D. I've just included Z and K for reference here. These are rated as multiples of IN. So 10 amps, multiple of 10 amps, 16 amps, multiples of 10 amps. The B overcurrent release looks somewhat like this. This is your thermal part, and this is your magnetic part where it trips. And just highlighted 0.2, 0.4, and 5 seconds because those are the common times required for TN systems, 0.4 and 0.5 actually. It will trip for between 3 to 5 times IN. For a C curve MCB, this is between 5 to 10 times IN. For a D curve MCB, this is between 10 to 20 times IN. For a K curve MCB, I put a star here because these are manufacturer defined. Sometimes they're 10 to 14. I've seen 8 to 14 as well. So this is just the general. Now what you'll, and there's also the D here, the Z here, which is 2 to 3 times. Now there'll be an interesting something you'll notice here is that for B MCBs, the same amount of current will cause tripping in basically instantaneous 0.1 seconds. So the current required to cause disconnection for 5-second disconnection, for 4-second disconnection, and for 0.2-second disconnection is the same. Same thing for C curve MCBs. But for D curve MCBs, 0.4 and 0.2 will have one value. However, 5 seconds will have a different value. So this will change the earth fault loop impedance. We'll get into that a little later. For Z, same story. Sorry, for K, same story. For Z, it is again the same value. These are again manufacturer defined, so it may differ per manufacturer. When it comes to the MCCB, let's focus on this curve here. There is the L, S, and I. The long time current is given as a percentage of the nominal current, and it is basically, so if you have a 100 ampere MCCB, I may choose to have it act as a 40 ampere MCCB. So I will say 0.4 times IN, that is my long time current. And then I can have a long time delay, which is if I have a high starting current in that circuit as an inrush current, it will delay the trip of the long time current for a certain amount of time to let that inrush current pass, to let that high starting current pass. If not, then it will trip after that time. Because you do not want these to trip prematurely and under fault-free conditions. Short time comes to when you have short circuits or earth faults of negligible impedance. You can say for short circuit currents between say maybe 6 to 8 times IN, there will be a delayed trip. This delayed trip can either be a fixed delay, so say a certain amount of time, or depending on the current, it will trip at a certain value. So that is the let through energy dependent characteristic. So if you look at this part of the curve, we'll just start from the beginning again. IR, you're changing essentially the overload current value. TR, you're changing the time it will wait to trip under overloads. ISD, which is your short time current, you're changing the tripping current for short circuits. And TSD, you're changing the delay. You're assigning a delay essentially to the short time current value here. And it can be either an I squared T characteristic. So depending on the magnitude of the short circuit current within those defined values, it will trip at a time, or you can have it fixed. It will just delay a certain amount of time and then go. Some circuit breakers also have the instantaneous setting, which means that if say you set instantaneous at 14 times IN, it will directly trip without any time delay because that current is so high enough that it could damage the circuit. So it will instantaneously trip without waiting. So I go back. See here, I've set an IR, I've set a TR, I've set an ISD and a TSD. This circuit breaker does not have an instantaneous value. But this is a very practical approach to this particular subject. Right. For fuses, like I said, these are defined by the manufacturers. If you look at IEC 60269, there's also an ISIC standard. They'll be given to you as current time, current peak current, current electrical energy, so on and so forth. Now, there are certain other characteristics. There is a cutoff or let through current. See, a lot of these circuit breakers and fuses, OCPDs, are what we call current limiting. What this means is that they will not allow the full fault current to actually pass through the circuit. We'll get into current limiting separately, but I'm just telling you here that as a characteristic of an OCPD, they say that this curve B is what I wanted to focus at first. If this is the prospective current, this will be the current let through without any protective device or without any current limiting. So, it will be just a 1-for-1 ratio. When the OCPD is introduced in the circuit, what happens is it is able to limit the magnitude of current, a fault current seen, and therefore the peak current seen. Therefore, there will be a lower value. Same thing for let through energy. I squared T is just a term used to describe specific let through energy. It is used for comparisons of the thermal stresses the cables are under. So again, A here is without current limiting or without the protective device. How much of a prospective current is there? That much of a let through energy is there. Once you introduce the OCPD, it is limiting the amount of fault current in there, and therefore the let through energy, which will define the amount of thermal stress. We'll look into this and calculating and coordinating this with the cable a little later. Now there is the energy class, which is only for B and C curve 60898 MCBs up to 63 amps, obviously. This is a simplified approach. If you look on the MCB, there's this little box here with 3 here, which is what I've circled. What this means is that for a defined MCB, say a C16 MCB, which is type C to 60898 part 1, there is a certain maximum amount of let through energy. So beyond this, whatever the fault current up to the ultimate breaking capacity, there will only be this much let through energy allowed in the circuit, which is what these current limiting breakers do, and energy classes are a simplified approach to that. Now, selectivity categories are interesting. So you got, let's say, a main distribution board supplying a building. Then per floor, you have individual floor distribution boards, and per load or per circuit, you have your RCBOs. What happens is, if there is a fault in the circuit, in a final circuit, say a socket circuit, you do not want the entire building to lose power. At the same time, you do not want the entire floor to lose power. So these upstream breakers, I will get into selectivity in greater detail later, have to have a time delay. There are circuit breakers that have a time delay, and there are circuit breakers that do not have a time delay. These are defined. So you see here, this breaker has a time delay. It's written CAT A, which is category A. Sorry, just one moment. I think this is the other way around. So, circuit break. No, yeah, sorry, my bad. Circuit breakers that do not have an intentional short time delay, and therefore they will have no rated withstand current. Circuit breakers at category B, they have a short time delay and they have a rated short time withstand current, which means that for a given short circuit, it will wait a certain amount of time, but the internal components are able to withstand that current and the electrical energy, and what is the rated short withstand current. When it comes to connecting our circuit breakers and fuses to our wiring system, you have the box terminal. This is what's seen in MCBs. The wire just goes in, there's a screw on top, it clamps down. You have the nut keeper, which is for lugs. The lug goes in, the nut and the nut fastens on. You also have the plug-in type circuit breaker, which is a different thing you see in some bus bar systems, where the MCCB or the fuse or the there are some MCBs also, they directly plug on to the wiring system. This is just for your reference, because oftentimes when you're specifying a project, you see 2 part numbers for the same tripping characteristic, same circuit breaker. Those part numbers actually correspond to the fact that one MCCB or one fuse or one circuit breaker has box terminals and one has a nut keeper terminals. Depending on the wiring system, depending on your infrastructure on site, you will then choose between these. Fuse systems, there are various fuse systems. We won't get into this in greater detail. Depending again on your structure and the system, you can choose a system. Now, when it comes to current limiting effects, we'll look at how this works. How does the circuit able to limit current? How this current limiting effect is seen under prospective fault current versus peak current, which is let through in the first half cycle, and the prospective fault current versus the let through energy for these current limiting breakers or fuses for them. Fuses are often current limiting. Now, see, if we look at the waveform of current versus time, let's just see. We all remember from basic high school that energy is equal to I squared times R. We have used to substitute impedance here, Z times T. Since the impedance when a short circuit happens is constant, we've assumed it to be constant. Energy is directly proportional to I squared T, which is our let through energy. So I plotted current against time just to give us an idea. It's actually, so energy would be, as the current increases, the energy increases in a square of that. For circuit breakers, they have something called they have some double rotating contacts which create repulsive forces between the fixed and moving contacts. And so there's something called repulsive Laplace forces that cause an arc to be formed, and the arc increases the impedance, therefore reduces the current. This happens very, very quickly. For a fuse element, the actual fuse element fuses, therefore there's an arc which increases the impedance and reduces the current. That's how the current limit. So if you look at this black line, this is a peak let through current without the current limiting effect. And the red line is the fault occurs peak let through current after the current limiting effect and the fault clears. So the amount of thermal stress, the amount of energy seen by the wiring system is greatly reduced. Therefore, this will greatly affect the cable sizing calculations and the amount of stress the system is put under. There's also the prospective fault current, which is given in root mean square, and your peak current, which is given in peak. So if we all know that, we say 230 volts RMS, the actual waveform, if we look at it on an oscilloscope, goes much higher. Basically, the way it works is that when it comes to circuit breakers tripping, you have to generally consider the peak current value, and once you come for long exposure, it is a prospective fault current in RMS. So if you want to do selectivity analysis, you want to see if an upstream breaker will trip, you have to look at the peak current value. Just ignore this A curve for now. This is something called asymmetric peak current. Generally, we look at symmetric peak current over a long amount of time. So see, without the breaker, there's a peak current and a prospective current and a peak current. This has a ratio, I believe, 1.414, which is root 2. With the circuit breaker or the fuse, this value is reduced. So we are able to essentially limit this. We go back here, we're able to limit this value, the peak current. This is obviously also provided as a prospective current RMS to let through energy for our cable calculations. Just keep that in mind. Again, without the overcurrent protection device and with the overcurrent protective device. You can see it sort of plateauing here. When it comes to ISI marking, or really this is status of compulsory registration, the ISIC 60898 MCB, if you're selling an MCB in India, it needs to be registered with, you need to have an ISI mark. It is comes under mandatory certification. There are actually 113 licenses fees for this, so this is a good thing. Unfortunately, when it comes to ISIC 60947 Part 2, currently the registration is optional. It is going to become, I believe, it's going to come under mandatory certification. There are actually 0 licenses. So you need to be really careful on the kind of breaker you buy, because you don't know essentially what you're buying, whether it is genuine or not. So stick with reputed brands. For 60269 Part 2, the actual fuse, it is optional, but there are 8 licenses, which is a nice thing. Now, coordination. How do we get OCP? We have 2 OCPDs in a circuit or 3 OCPDs in a circuit. How do we make sure that only the ones closest to the fault trip? That is selectivity. Then, if one OCPD is there and you have a fault downstream of that, and the fault is having a greater there's a greater fault current than what the breaker or the OCPD can handle. How do we ensure that there's no damage? That is called backup protection or cascading. So when it comes to coordination, we look at what does coordination consist of? As we said, this is selectivity plus backup protection, or what was earlier known as discrimination plus cascading. We look at requirements of selectivity. How do we achieve these things? We look at figuring out how to verify if there is selectivity present between 2 overcurrent protection devices by something called desk study, which is a comparison of these characteristics. We look at verifying selectivity from manufacturer data, and we look at requirements of backup protection. Backup protection is a little more complicated, so you can only really verify it from manufacturer data alone, not by desk study. So we look at Annex A, Section 14, Part 1 of our National Electrical Code of India. It will say that there is something called coordination that is a requirement in electrical installations. It is made up of selectivity and backup protection. Simply said, selectivity means only the OCPD closest to the fault interrupts the current. You have continuity of supply in all upstream OCPDs and all upstream circuits. Backup protection is the OCPD closest to the fault is assisted by an upstream OCPD in clearing that fault. We look at some examples. For the purpose of coordination, remember when I refer to OCPD 1, it is the breaker or the OCPD closest to the fault, which is considered as a downstream breaker. and OCPD2, which is the OCPD immediately upstream of this. So let's say supplying this OCPD. So let's look at an example here. I've got my three-phase and neutral supply. I've got a MCCB here. My wires come down here. I've got a main circuit, main and distribution board. I've got an isolator here. I've got two final circuits, two distribution circuits, sub-main circuits. And then I have got from the distribution circuit, sub-main circuit, I have got an RCBO going to, let's say, a lighting circuit. If we have, say, situation one, a fault on the distribution circuit here, we do not want other distribution circuits to lose power. We do not want this breaker to trip. We only want this one to trip. This is called selectivity. Case number two, we have a fault on this lighting circuit. We do not want the other, there are other circuits here. We do not want these to lose power. We do not want this breaker to trip. We only want this breaker to trip. This is what you call selectivity. Only the breaker closest to the fault or only the OCPD closest to the fault disconnects. Could be a fuse also. Overcurrent selectivity, as defined by clause 3.7.23.1 in IEC 6094-7 Part 1 2020, is the coordination of the operating characteristics of two or more overcurrent reduction devices such that in the incidence of overcurrents within a given limit, the device intended to the one device is intended to operate within these limits, while the other, which is the upstream breaker, does not do so. So if I go back here, if a fault is here, only this RCBO should disconnect. This MCCB should not disconnect, and this MCCB definitely should not disconnect. Or if this distribution circuit has a fault, only this distribution circuit should lose power, not the circuit breaker that protects the entire supply to the installation. Now, overcurrent selectivity. So overcurrent is made of overloads and fault currents or short circuits. So therefore, overcurrent selectivity is made up of overload selectivity plus fault current or short circuit selectivity. When we talk about selectivity, either we have total selectivity, which means the upstream OCPD, so if there's a fault here, will not trip for all values up to ICU of this. So if there are faults up to ICU in this circuit, only this breaker will trip. This breaker will not trip. So their total selectivity achieved up to ICU of this circuit breaker or overcurrent protected device. Partial selectivity means the upstream OCPD2 is selective up to a certain prospective fault current. So say this if there's a fault here and this circuit breaker is immediately upstream of this and this circuit breaker is upstream of this circuit breaker, I am saying that for faults up to 4.5 kiloamperes, only this OCPD will trip. For faults greater than 4.5 kiloamperes, this OCPD will trip. That is called partial selectivity. And obviously, these can only be defined up to the total, the ultimate breaking capacity of this device. If you have a fault greater than the ultimate breaking capacity of this device obviously has to trip. Otherwise, there'll be damage to the protective device. There'll be arcing. You'll have a lot of damage. That's a whole mess. Just remember that. So when you say total selectivity, it's only up to ICU, ultimate short circuit breaking capacity of the immediately upstream protected device. How we achieve overload selectivity is very easy. We compare the magnetic part, essentially, the long time part of the two overcurrent protecting devices. If there is separation, so for a certain overcurrent, this will trip in this much time, this will not trip. First, over here, this will trip in this much time, this will take a lot more time to trip. So the times are far enough for the upstream OCPD to not disconnect. In the case of fault currents, you see, they are too close because it's a logarithmic graph, remember. These values are insanely close to each other. There is not enough separation. Therefore, you have to do a depth study. You can ignore the fact that these are both circuit breakers, by the way. This could be a fuse and a circuit breaker, or a circuit breaker and a fuse, or a fuse and a fuse, for that matter of fact. Remember, like I said, OCPD1 is the one closest to the fault. OCPD2 is the one upstream of this OCPD1. This is adapted, by the way, from figure A2 of IEC 60947 Part 1, 2016 plus Amendment 1 in 2019. So, how do we determine whether there is selectivity? See, if OCPD2 is a circuit breaker, we have to compare the peak current corresponding to the instantaneous current setting of OCPD1, and we have to make sure this is lesser than the peak let through current corresponding required to cause instantaneous tripping of OCPD2. So we'll go back to the diagram here. When there is a fault here, we need to ensure that the let the current here, the peak current on the first half cycle is not enough to trigger a trip here. Plain and simple. We'll get these values from the manufacturer. I'll show you an example as well. That is very easy. If OCPD1 is a circuit breaker and OCPD2 is a fuse, fuses we have to compare the let-through energy. We have to ensure that the current limited I square T value corresponding to OCPD1 tripping is less than the pre-arcing I square T value of OCPD2. So we'll go back here. When there's a fault, we have to ensure that the let-through energy here under the fault is less than the let-through energy, the peak let-through energy required tripping here. I will repeat. The current limited I square T value corresponding to OCPD1 is lesser than what is called a pre-arcing, just before it arcs, the fuse, I square T value for OCPD2. I'll show you an example here ahead. Time-based selectivity also exists. So simply you have a delay on this MCCB. So it will wait for this RCB to clear the fault. If it doesn't clear the fault, then it will trip. So that's where you have the selectivity categories, and you have a defined ICW. The MCCB and the internal components can withstand that time of current. So simple, there's a short time delay, and assigned for relevant short time current, it will wait. Very importantly, ICW is given by the manufacturer, but the whole wiring system needs to be able to withstand the full let-through energy for this duration. It could be even 0.05 seconds. This calculation needs to be done. I'll show you how to do it as well. Now, when it comes to this, like I said, we need to find out the peak current corresponding to the instantaneous tripping setting of OCPD1, which means when this, say, RCBO or MCB trips, how much energy is it going to, what is the peak current that this circuit breaker is going to see, this wiring is going to see. This is given as a graph. Look at this B line here. The manufacturer will tell you, and they are required to tell you, as per if they comply with 60947, that for a certain prospective current, this is the peak current that will be seen by the system. C is for a current limiting device. So keep this into mind. So say if I have got 100 kiloamperes, this is obviously you're coming into ACBs and stuff like that, or say 10 kiloamperes. This is the amount of peak current that will be seen by the upstream circuit breaker and wiring system. This value has to be less than the minimum peak current causing tripping. Okay. Now, say I've got an MCCB that is set to trip at 5000 amp. So for instance, say it is a 500 ampere MCCB and it is set to an instantaneous tripping setting of 5 times 10, so 5000 amps. It's important to know that in these adjustable circuit breakers, 60947 requires us to take into account a tolerance of plus minus 20%, which means the minimum peak current can only be calculated when we multiply this by 0.8, which is 20% less. So we take 4000 amps. So 5000 multiplied by 0.8 is 4000. This is now in root mean square, but we want it to be peak current. Therefore, we take it and multiply by 1.414. That is the ratio of the peak to the RMS value. Therefore, we get for 4000 amps of RMS, the peak current value is 5656 amps. So we need to make sure that this particular RCB, this particular MCB does not release more than 5656 amps peak. There's a difference between peak and RMS. If that does not happen, the upstream protective device will not cause disconnection. So our requirement for selectivity is satisfied. Obviously, this is a lot more complicated process. So very often the manufacturer will give you a table. Now this is for OCPD of circuit breaker, or for, yeah. If you have a fuse, so basically, yeah, the current limited I square T value corresponding to OCPD1 shall be lesser than the pre-arcing value. So how much I square T will this release when it trips, and how much I square T will this have just before it blows? So once again, we'll find out the current limited I square T value. You can see now why current limiting is becoming so important, especially for selectivity. You get this value corresponding to the relevant prospective current. This we know, we can calculate, we can even measure. This is the limited let through energy. And what is the pre-arcing let through energy for the fuse? This is given by the manufacturer and the standards. So say for a GU fuse link, 100 amperes, the minimum I squared T is going to release, pre-arcing is going to be 12. Now there's also a maximum. We have to take the minimum because we have to assume the most onerous conditions, which is what value will this definitely, the lowest value what it will arc. So if we know that from this B curve, the value of limited let through energy is less than say 12, this is times 1000 amp squared seconds, then we achieve selectivity for this arrangement, plain and simple. Obviously this is a complicated process, so a manufacturer will give us this data. They will say, this is from Legrand by the way, for this MCCB and this MCB, selectivity is achieved to this value. So for a say 100 ampere MCCB and a 16 ampere MCB downstream of it, you will achieve total selectivity up to 16 kiloamperes. If it is a 32 ampere MCB downstream, selectivity is achieved up to 4 ampere. These values, these are available for all manufacturers. Some manufacturers even have specialized software where you can do this. Backup protection is a little interesting. So say I've got this, this is my distribution circuit, this is my main circuit, and this is the from the distribution circuit, this is the final load, this is the lighting circuit. Say I have 9 kiloamperes of fault here, but ICU or ICN for this circuit breaker is only 6 kiloamperes. Now, this can obviously not clear this fault without damage, but this is related to 15 kiloamperes. What may happen is that this 9 kiloamperes fault may only be seen towards faults that are happening very much near the circuit breaker. For faults away, this is not really an issue. And say this is an armored cable or that, I mean, the possibility of faults are much low here. However, we need to ensure protection. So this breaker will essentially help this breaker or this OCPD will help this OCPD clear that amount of fault. Obviously, this only works when up to the you need to ensure that this value here. Sorry, 1 second. Yeah, this value is what's happening is this value is greater than this value, but not lesser than this, but still lesser than this value. Backup protection as per clause 3.7.23.1 of IEC 64947 part 1 defines backup protection as overcurrent coordination of two overcurrent protected devices in series where the protected device generally, but not necessarily on the supply side, affects the overcurrent protection with or without the assistance of other protected device. So if you're having assistance and prevents any excessive stress. You're preventing stress on this. Now, for backup protection, we have something called a takeover current, which means for a certain, after faults of a certain current seen by this OCPD, this will step in and help clear the fault. That's simply take-up current. Prospective fault current at which OCPD will disconnect the circuit for the purposes of backup protection. And then you've got the ultimate short circuit breaking capacity of OCPD1. And this is a value of prospective fault current which OCPD1 can safely disconnect. Obviously, backup protection shall only be provided when the takeover current is lesser than or equal to ICU, because we do not want a situation where this is only taking over, say, when this reach 8 kiloampere. Then this is going to have an arc, this is going to be messed up, and you're going to have a lot of damage to your system. Just keep that in mind. This is not easy to do with desk study, so it's very easy. Manufacturers will provide you a table. This is from Eaton, for instance. This will say for this particular MCCB upstream, for a type C 20 ampere, the takeover current is 23 kiloamperes, plain and simple. Okay, so how do we achieve fault protection via OCPDs? The basic idea is we have fault protection, which is a protective measure. We look at disconnection times under fault protection, how the overcurrent release and earth fault loop impedance relates to this, and the relation to the thermal stresses of the fault current, which is your I squared T value. Remember, again, I'm just recapping here. This is what we in NFE, Mr. Gopakumar always hammers down, is that fault protection is protective earthing plus protective equipotential bonding plus automatic disconnection of supply through the OCPD or RCD for TTs. OCPDs are used to achieve fault protection, but they are only achieve the ADS. These two have to still be there, protective earthing and protective equipotential bonding. That's only when you are achieving fault protection. The objective is we want to limit during fault conditions the magnitude and duration of voltages that may appear between exposed and extraneous metalwork and the true earth, which is essentially we are establishing what is called an equipotential zone. The protective earthing provides this zone a 0 volt reference and therefore to the general mass of earth, and the equipotential bonding creates the zone. Generally, for normal installation, this is 50 volts, and the automatic disconnection of supply through the OCPD will disconnect the power and remove the fault current that is causing a voltage difference. Plain and simple. This is what we are focusing on here. We all know that if you look at IS 732 regulation 4.2.11.3.2, the OCPD shall cause disconnection to limit the duration of touch voltage caused by fault currents. For final circuits in TN systems, this is 0.4 seconds. For final circuits in TT systems, this is 0.2 seconds. For distribution circuit, this is 5 seconds for TN systems and 1 second for TT systems. The ADS will only limit the duration of the fault. The bonding will limit the magnitude. This is just an image to show you that we connect to the MET all the individual class 1 equipment, the DBs, equipment casing. There may be protective supplementary equipotential bonding, and we obviously bond the gas pipe and structures, which are extraneous conductive parts to the MET, which is then connected to your star pointer transformer. You may also have an electrode on site. Now, if we look at our overcurrent release, we know a B curve MCV traces between 3 to 5 times IN. For C, it is 5 to 10. For D, it is 10 to 20. Now we need to say what current will the OCPD definitely trip under. So we assume the higher value. For B, it is 5. For C, it is 10. For D, it is 20. Now we go back here. If you remember from earlier, for all these values, for B, there is only a single current causing disconnection because it is instantaneous, 0.1 second. For C, same story here. But for D, there's a different value for 5 seconds. So, when it comes to earth fault loop impedance, clause 4.5 of section 18, part 1 of our National Electrical Code of India says, ZS, which is your earth fault loop impedance, shall be lesser than or equal to 2 by 3 multiplied by UO into IA. We're just basically seeing this is a voltage across the circuit. This is the current causing this operation of the OCPD, the instantaneous operation. And we're assuming a safety factor of 0.66 just to ensure that we leave a buffer. Okay. Now, what this means is that for a particular circuit breaker, say 20 amps MCB type B, the maximum earth fault loop impedance measured has to be 1.53. For type C, it becomes half, 0.77. And for type D, it becomes even half of this, 0.38. Remember, this is only for 0.4 second disconnection. If, for example, a D curve MCB is protecting a distribution circuit and you require 0.5 seconds, there's a different time that has to be calculated. This data will be again be given to you by the manufacturer. Keep this in mind, because only if these values are met will the breaker disconnect, and only then will you have all this current limiting and all this stuff that's happening. Without meeting these values, none of this is going to be achieved. So this is a fundamental requirement. Okay, another important thing is requirements of fault protection. Just by achieving these loop impedance values, it does not ensure that the cables are not going to be damaged by the electro energy caused by the faults. So this is the thermal effects of fault current. Protection against the thermal effects of short circuits or earth faults of negligible impedance basically is what we're going to look at. This is broken into 7 sections. Firstly, what does the standard say? Then what are the cable temperatures that are achieved during faults? How is a fault current created? How do we calculate these fault currents? How does this tie into the adiabatic equation? And what this has to do with the OCPD electroenergy characteristics that I showed you earlier. And we'll do a sample thermal withstand analysis. This is a cable that has been badly damaged, by the way. If you look at IS 732 and NEC clause 4.4.5 of IS 732 and clause 4.4.6 in section 12 part 1 of NEC says, for cables and insulated conductors, all currents caused by a short circuit occurring at any point of the circuit, this is very important, any point of the circuit shall be interrupted in a time not exceeding that which brings the insulation of the conductors to a permitted limit temperature. When we talk about these temperatures, we assume an ambient temperature of 30 degrees. That is what the cable is at under no load, depending on the surrounding temperature. The operating temperature is, say, if the cable is loaded to a certain percentage of its current carrying capacity, it runs at a certain value. The maximum operating temperature is this can only run to 70 degrees. The limiting temperature is what temperature the cable will achieve in point, the copper inside the cable and hence the insulation will achieve in this 0.1 seconds. This is 160 degrees Celsius for our PVC cables. Now, how are fault currents created? If this is our transformer, you've got a Y here, RYB. This is consider this single phase. This is our point of commencement of supply. We've got our overcurrent protection device, our neutral and our protective earth. When a fault occurs, either through line to neutral or line to protective earth, there is essentially a fault of negligible impedance that occurs, and the magnitude of this earth fault current depends on the resistance and impedance of these wires. The maximum fault current will occur if the fault occurs closest to the transformer, which is here. The minimum occurs if it is here. So to calculate, we need the loop impedance values for here for the maximum and here for the minimum. How do we calculate this? Basic Ohm's law, I is equal to VR, V by R, we'll just substitute it by Z. For earth fault current, this is the earth fault loop impedance at the source plus R1, which is the resistance of the line conductor, plus R2, which is the resistance of the protective earth conductor. For prospective short circuit current, it is loop impedance between line and neutral plus R1 plus Rn. This value ZE, ZLN, the loop impedance for short circuit and for earth faults can either be measured or it can be inquired or calculated based on the transformer if you have that. R1, R2 or Rn can be calculated either from IEC 60287, but if you buy your cables from a good manufacturer, this data will be given to you. Okay, we look at IS 732 part 4.4.5, clause 4.4.5 and clause 4.4.6 of section 12 part 1 of the National Electrical Code. It tells us that T shall be equal to K squared S squared upon I squared. This T is essentially the duration in seconds in which a fault has to be interrupted as provided by the OCPD manufacturer or the product standard. So this is basically saying that for a given fault and a given cable, this is the time, the maximum time that the fault has to be interrupted in. If the breaker or the OCPD disconnects in a time greater than this, there will be damage to the cable. S is the cross-sectional area of the conductor in square millimeters. I is the fault current in root mean square value, that's the RMS values. Account being taken of the current limiting effect. So if you remember, we'll just rearrange this equation. I'll show you something magical. And K is a factor that is given for the table for the cable depending on the resistivity, temperature coefficient, and heat capacity. This is in National Electrical Code. I'll show you. If we rearrange this, we will get that I squared T shall be lesser than or equal to K squared S squared. If you remember, this I squared T value corresponds to the let-through energy, which is given by the manufacturer of the OCPD. The let-through energy in a fault has to be lesser than the thermal withstand of the cable. K squared S squared can be calculated. I'll show you how. And this has to be done for all current caused by short circuits occurring at any point of the circuit. So, I squared T taken due account of the current limiting effect is given by the manufacturer. So, they will tell you for a certain amount of prospective fault current, this is the let-through energy. And this is given for the full range of prospective fault currents. Now, we'll do a sample. A load is protected by a 32 ampere Beaker ISIC 60898 MCB. The measured line to neutral impedance at the origin of the circuit is 0.1 ohms. The length of the cable required from the origin of the circuit, which is the point of commencement of supply, to the load is 45 meters. A 6 square mm IS 694 cable conductors are class 2 as per IEC 60228 or IS 8130 is being considered to be used. Perform a thermal withstand analysis to determine if the cable is suitably coordinated with the OCPD for protection against short circuit. There was somebody that asked us, "Hi, how is the multiple circuit breaker selection with respect to short circuit in the same circuit?" This is how you do it. So I'm telling you that the line to neutral loop impedance is 0.1 ohms at the origin. So IPSCC max is going to be 230 volts divided by 0.1 ohms, 2300 amps, which is the fault current here. Then, based on information that I have from IEC 60228, I know that a 6 square mm cable has a resistance of 3.08 milliohms per meter. It is running for 45 meters and it is running at, there's a line and a neutral, so you'll multiply by 2. This 1.2 factor takes into account that the resistance value is given in IEC 60228 and by the manufacturer for the cable are given for cables at an ambient temperature of 20 degrees. In a fault, we have to assume a worst case scenario that the cables are running at maximum operating temperature. So this 1.2 corrects the resistance to 70 degrees. This is just a unit conversion. When we multiply 3.08 into 2 into 45 into 1.2 divided by 1000, we get 0.4324 ohms. We have to obviously add this to 0.1. That's why we get this. So 0.1 ohms here. We know that this is 33264 plus 0.1 at the point of commencement of supply. Oops. So let's just say 0.3. So 0.1, 0.33. So 0.43 is what we get here. Now, then given the short circuit loop impedance, line to neutral loop impedance, at the end we do 230 divided by this value and we get 531.61 amps. Let's just call it 530. It's a minimum, so we'll round it to 530. So now we have our I values at the beginning, at the end. S is known. How do we get K? If you look at clause 4.4.5.5.2 in the national IS 732, it tells you that for a thermoplastic PVC cable, for a cross-sectional area less than 300 square millimeters at an initial temperature of 70 and a final temperature at 160. Remember, this is our in load, in fault. This value for copper is 115. So K squared S squared is going to be 115 squared times 6 squared is 476,100 amps squared seconds. Now, we'll go on the graph. Purple line denotes the minimum fault current, which is our 531.61, which we just calculated. Blue dotted line denotes 2,300 amps, which is our maximum fault current at the point closest to the commencement of supply. The black dotted line denotes this value, 476,100. The red line is the let through energy characteristics of the breaker. We need to make sure that for areas between the purple dotted line and the blue dotted line, the let through energy given by the red line is always lesser than the black dotted line. This line shall always be lower than this line for areas between this line, which in this case is satisfied. Cases when, now remember, I ran this calculation for line to neutral loop impedance and short circuit. However, for earth faults of negligible impedance, this has to also be run given earth fault loop impedance at point of commencement of supply, add the resistance of the wires, and calculate the earth fault loop impedance at the extremity and rerun this analysis. The process is the exact same, just a different calculation is required. Case number 1, where thermal withstand analysis will fail. When you do these calculations, you will realize that your cable is not sized properly or your breaker is rather oversized. For maximum prospective fault currents, which are faults that occur closest to the breaker, the value of let through energy released by the circuit breaker is greater than what the cable can withstand. Therefore, for faults towards the point of commencement of supply towards the circuit breaker, the cable will be damaged. The cable essentially cannot withstand the electrical energy caused by a short circuit. I'll give you an example. I was at a site in Hyderabad, and it was a building, and the building's demand was about 100 amperes. They put a 35 square millimeter cable, which is more than enough to what the cable can handle. However, the short circuit protection device was a 630 ampere MCCB set to times 10. This is a situation where you're going to see that the cables are big, but the breakers are oversized so much that the fault current is not going to be effectively current limited by the breaker, and you're going to have damage to the cable. This is a far more common situation where there is just not enough fault current for the device to disconnect. So if you look at this green line, this is the earth fault, minimum earth fault, maximum earth fault loop impedance, and minimum current causing instantaneous operation. This is actually, sorry, one moment. This is actually more than the minimum. So you can have at extremities currents between these two values where where the overcurrent protection device will simply not disconnect. This is your very long cables or undersized cables. So there is this. So basically, if we go back, this is not being satisfied essentially. So from a thermal withstand point of view, if your maximum earth fault loop impedance values are not satisfied, we are going to turn into case 2. Anyways, this was about that. I think we are running out of time. So protection against overload current I've presented many times at the NEC web events as well. So I will end the presentation here. Are we good on time?
Yes, probably a few more minutes.
Okay, few more minutes. Okay. So this is a very vast topic. So I'll delve into the specific points that enter into the that get into the what's it called, that get into the tie in with the actual devices. See, what do the standards say? We look at that. How we calculate a current carrying capacity from a tabulated current carrying capacity. How this has to do with cable maximum operating temperatures. How we protect against overload currents. How we derate IT, which is a tabulated value, to IZ, which is a current carrying capacity in the continuous service. We look at ambient temperatures, how these derate. If you have a higher ambient temperature, the current carrying capacity is reduced. Grouping, if you have many circuits grouped together, how the current carrying capacity is reduced. What the soil thermal resistivity is. If you have a cable buried in the ground, the ability of the cable to dissipate heat is affected. Fusing factor, which comes into a conventional tripping times. This is what I'll focus on today. Okay. Going back to our conventional tripping times, we will see that HRC fuses have a fusing current of 1.6 IN, which means that for say a 10 amp HRC fuse, 60269 fuse, in an overload condition, it will trip at 16 amps in 1 hour. But IS 732 clause 5.2.6 and clause 4.4.4 specify that I2 shall be lesser than or equal to 1.45 times IZ, which means the current causing effective operation, the conventional tripping current or fusing current, shall be lesser than or equal to 1.45 times IZ. If the circuit is running at full operation, IZ would end up, we need the IZ to be equal to the IN. This is the worst case scenario. A 1.4 fusing factor is all that is acceptable as per this. However, for an HRC fuse, this is 1.6. So we need to derate the cable. That's just something to keep in mind. And then the cardinal requirement. IB shall be lesser than or equal to IN shall be lesser than or equal to IZ. This is interesting. Very common, I've heard electricians say, if you have a certain load, we put a certain cable. Say 13 ampere load, we'll just take a cable that can say take 20 amperes. Safe. Absolutely not safe. You're forgetting about the breaker, which is this IN. IB shall definitely be lesser than or equal to IZ. IZ should definitely be greater than or equal to IB. However, in between, you have to have a protective device. So if I have a 13 ampere load, which is our design current, IN can be 16 amperes, but the current carrying capacity under continuous service, which is derated, has to be greater than the value than IN. This duration is important because electricians on site often say if it's a 2.5 square mm cable, it can carry 20 amps. And they will just say 20 amp is greater than 16 amps or greater than 13 amps, the inequality is satisfied. No. We need to ensure that it is greater than or equal to IN after duration. And also, I2 shall be lesser than or equal to 1.45 times IZ. Duration factors in IS 732 and NEC are recognized as four. There is a rated factor for grouping, how many cables are bunched together, how many circuits are bunched together, which will affect the ability to dissipate heat. You'll find this information in S4 and S5 of IS 732. This is an Annex S, by the way. The rating factor for ambient temperature. See, these cables, let's say PVC cable, will run at 70 degrees Celsius, maximum operating temperature. And let's say the ambient is 30 degrees normally. So it can rise up by 40 degrees. However, if the ambient temperature is say 45 degrees, then the temperature rise is only 25, 70 minus 45. Therefore, aeration is required. If you bury the cable in the soil's thermal resistivity will also affect the ability of the cable to carry heat. If the device, the OCPD, has a fusing factor greater than 1.45, it's a rewirable fuse or HRC fuse, once again, duration is required. So, normally this is an interactive session, but because this is a webinar, that is a very difficult thing to do. But anyways, grouping factors are given as per the installation reference method and the number of circuits grouped. Ambient temperatures are given as per the ambient temperature and the kind of cable. Soil thermal resistivity are given as per the thermal resistivity of the soil and the method of burial. Is it buried direct or in a duct? And also what depth is it buried to? And of course, we've got the fusing factor. Now, since fusing currents up to 1.45 times IN are acceptable as per regulation 444.1 of IS 732, a correction factor must be used for overcurrent protection devices with a fusing factor about 1.45. Now, HRC fuses are very common. They have a fusing factor of 1.6. So 1.45 divided by 1.6 is 0.9. MCBs to 60898 are having a 1.45 fusing factor, so there's no duration required. If you have an MCCB, then you need to refer to your TR and your IR value. This will tell you for what current will it trip in what time. Accordingly, you take 1.45 divided by that IR, which is as a proportion of the nominal current, and then usually this is times 6, by the way, you arrive at this. So this is to do with your radiation factor for fusing. Let's just run through a sample calculation. A 90-degree XLP IS7098 two-core cable has to be buried in an underground duct at a depth of 0.7 meters. The surrounding soil has a thermal resistivity of 3 degrees Kelvin per meter watt. The cable is laid along with 3 other equally loaded cables. The ambient temperature of the soil is 40 degrees Celsius, and the cable will be protected by a 16 ampere IS2086 rewirable fuse. We need to find out what the minimum cross-sectional area of the cable is that can be used. We'll just rearrange the formula a little bit. We'll assume IZ is equal to 16 amperes. Worst case, 16 divided by CG, CA, CF, CF will give you the minimum tabulated value required. So you cannot just choose the value that will actually carry 16 amps. You have to choose a value that is greater than 16 divided by this value. Okay. I said there were 3 other circuits. That is totally 4 circuits. The cable is embedded in a surface. So it's ref item 1, 0.65. I'll just plug that value in right here. Now, the ambient temperature of the ground is 40 degrees Celsius. See, the important thing when it comes to cables is that we need to find out what the maximum operating temperature the cable can operate at, which is dependent on the insulation. However, just because the cable insulation can withstand, say, 90 degrees in XLP, does not mean that the connected equipment, the terminals of the MCCBs, terminal blocks, so on and so forth, can also withstand this value. So, unless we have information that specifically tells us that the terminals and connected equipment can withstand 90 degrees, we have to assume 70 degrees. So, use the PVC factor even for an XLP cable. So, this is 0.77. So plug that in right there. Soil thermal resistivity. I said 3 degrees Kelvin per meter watt. Buried cable depth, it is in a duct, so it is directly buried, so 0.96. 0.96, there we go. Fusing factor, this is a 2086 fuse. It has a 1.9 IN fusing factor with a conventional tripping time of 30 minutes. Therefore, I'm terribly sorry. 1.6 and 30 minutes. From the previous page, we'll put in 0.75 because 1.45 divided by 1.9 is 0.75. Yes. Hold on, I'm sorry. Yes, sorry, it is 1.9, not 1.6. So that's 0.75. Therefore, we know that we need the cable to carry a tabulated current carrying capacity of 44.41 amps. So you see, for a circuit that traditionally the traditional mindset is to choose something that will just carry more than 16 amps as the load current. We actually need a cable that can carry 44.41 amps. So where normally they say an electrician would have specified 2.5 square mm, for reference method D1, you can see you actually need a 6 square mm cable. So that is where the duration comes in. So therefore, we take a 6 square mm value. Anyways, that is the end of this presentation. I hope that was helpful. We can take questions now.
So we have few questions. Okay, a lot of questions are there. Some of the questions are not related to the subject, which I already removed. And there are few questions which we have to answer. I
Okay.
will start from the one. How the multiple circuit breaker selection with respect to short circuit current in the same circuit, like upstream, downstream. I think you have already replied it, so no need to reply that.
Yeah, that's
Uh,
been answered.
the next question from Mr. Vignesh is, can I use 1000-volt rated cable for 1200 voltage and the current will have be less than 0.5 amps? This is also, I don't think that this is 1000-volt rated cable for 1200 volt. Of course, you cannot use it. If the cable
It's
is said
not.
1000 volt, then you have to use it below 1000 volt.
Yeah, he's
So,
saying that the current is lesser, but the point is the insulation is not rated for that value.
yes, of course. Then how the circuit breaker selection based on short circuit current, based on upstream and downstream circuit. I think this you already
This is already
explained.
answered.
It
Yeah.
was in 1137. You explained it after that. Somebody was asking to repeat the concept of
Yeah.
ICU and ICS. Probably the
Yeah, sure.
explanation, since we are sharing the video, we would like to recommend you please go through the video. And then once when you go through the video, you can also type the comments under the video so that this can be again answered. We will clear all your doubts. Please don't worry about it. There is a simple question, which is better, fuse or MCB? Probably, Krish, you can answer this.
It is not a question of which is better, it is a question of the utility of the circuit. So, see, for instance, if you have a very high fault current, an MCCB will be very expensive to buy. An MCB simply will not be able to cope with it. In that situation, the fuse is a better choice. But remember, the possibility of adjustability and future changes with a fuse will ever change the fuse. With an MCCB, you can set a delay and do all these things. So it's not a simple yes, fuse or MCB answer. It is a question of the utility of the circuit. Which is why I encourage you to read manufacturer's data sheets, understand the tripping characteristics of the fuse. If the question is a simple, which is better, fuse or MCB, for industrial and for distribution, fuse is definitely much better.
Yes. Okay, now there is a question. Somebody made a comment. In fact, it's not a question. I think I squared RT should be there instead of IZT, except DC system where the reactance is 0.
Yeah. So the thing is that Z is a simplified term used. If you want to perform a more accurate, this is for let-through energy, right? So if you want to perform a more accurate description, I would say you can consider you break down impedance into resistance and reactance, and then you run the calculation.
Okay, good. Now there is a comment. It's not a question. If you can show the marking on breakers suitable for isolation, I think it is a
Yeah,
good
yeah,
idea
yeah.
in future to include the symbols of each of these devices.
Yeah. I will just 1 minute. I will show you actually. I have a symbol here. 1 minute. Just hold on. You can take the next one till then.
Yeah. So, what important precautions considering earthing, leakage current continuity has to restrict the outage of specific equipment, such occurrence? Actually, the question is not clear. Anyway, Mr. Sharma, regarding earth leakage and earth fault protection, we have the program next week. Please do join us next week the same time, 11 a.m. We will explain this particular subject, which will be more opt. Then the next question, can you explain let-through energy of circuit breaker in detail, please? Why cable damaged? Okay, Mr. Akash, the best way is you please go through the videos in our YouTube channel. It will be up in the YouTube channel probably in another 20-30 minutes or maybe half an hour. You can go through the video and put the questions under the YouTube itself so that we will be able to answer. Mr.
Yeah,
Giridhar, for a 100 kVA distribution, for a 100 kVA distribution transformer, LT side current is around 131 amps. What size of MCB, MCCB fuse we shall select?
Well, that depends entirely on the cables and the loads. You will have to perform the analysis. It's not a simple yes or no answer. This is the symbol, by the way. I think Mr. Amrit Lal had asked. There's a symbol marked.
No, that is okay. What we can't see that in the phone. The best way is
Oh.
in the next webinars onward, we have to put it on the slide
Okay, fine.
of symbols because this is also sometimes a big confusion for people. So
Okay.
then somebody is again asking what is the difference between switch fuse unit and fuse switch unit?
So, okay, that is a very interesting question. One of them breaks the circuit, one of them pulls the fuse out. So, that is the difference. If you want, please refer to 60947 part 3 and you can find detailed information on that.
Okay. Now, Mr. Kamlesh
That's
has
a very
asked,
interesting question he's asked.
yeah, let I have measured the available prospective fault current and I wanted to select a breaker when
Okay,
then
no, that's a different one. Yeah. Sorry.
application what I should consider breaking capacity or marking capacity because prices are different in both cases. What is relevant for safety point of duty cycle OCOOC?
See, the making, I think, I don't know what you mean by marking capacity. It's making capacity. Yeah. You have to look at the braking capacity. You have to look at the ICS value, which is the braking capacity in service. The making capacity is not relevant for a designer as such. You need to look at the ICS value, in service braking capacity value.
Yeah. So now, as you have considered adiabatic situation while calculating the thermal damage the curve of cable, but in practical situation is non-adiabatic.
Yeah. So
In this,
see,
yeah,
may I answer?
yeah,
See, for faults interrupted in a value in a time of 0.1 seconds per millimeter squared, the adiabatic calculation is valid. which means for a 10 square mm cable, the adiabatic equation is valid for faults that can disconnect in 1 second. The difference between adiabatic and non-adiabatic is an adiabatic assumes that there is no loss of heat to the surrounding. All the heat and thermal stress is contained within the cable. A non-adiabatic assumes that the loss of the heat will reduce the thermal stress in the cable. If you want information on non-adiabatic calculations, I will refer you to an IEC standard. I'll give you the number right now. However, in fault current scenarios, the calculation will be adiabatic because your disconnection is going to happen in 0.1 seconds per millimeter squared. So there is no correction factor required there. I'll give you the standard in a moment. So
Okay, by the time
Yeah, so it is IEC 60949.
okay.
That for non-adiabatic heat transfer and short circuit rating.
So Kamalesh, probably you must have noted it down. It would be difficult for us to type because there are so many questions. Let us go to the next question. If 10.5 kA is if 10.5 kA is short circuit of a 500 kVA DG, what is the capacity of ICM and ICU of breaker?
Sorry, let me just read that question again. If 10 is short circuit, well, obviously you would need a breaker to have. ICM is not really that important here. And ICU is also not important. And ICS of greater than 10.5 kA. So ICS is important, not ICM or ICU in the situation. ICS has to be greater than 10.5 kA.
Okay.
And 10.5 kA is a very easy value to, you can get easily 16 ampere switch ICS breakers. That's not a problem at all.
So there is a question, life of fuse is much lower. Is it correct? So life cycle cost of MCB is better. Please advise.
Well, if your fuse keeps blowing, something is seriously wrong in your circuit. So I would not recommend that you decide to choose to an MCB instead of a fuse for that reason.
Okay. Sometimes people use MCB isolator instead of MCB and vice versa. Okay, it's a statement, not a question.
May I respond to that though?
Yes, of course. Of course.
See, this is a very interesting subject because very often, see, when you come to selectivity, it's very important to have this coordination done. But when we have sometimes in installations, people use MCBs to do switching. What will happen is you lose selectivity here in this case. What you need to do is use an isolator there. So, for instance, if I have an air conditioner protected by, say, an MCB, there is at the distribution board, there is no need for another MCB at the pointer of the actual air conditioner. A simple rotary isolator can be installed there. But in practice, a lot of people are putting MCBs there. Then when a fault occurs, both will trip. And also sometimes it lulls people into a false false sense of safety. Alternatively, you have a lot of cowboys that put isolators instead of MCBs to control to protect circuits, which will achieve nothing. So just please keep that in mind.
Yes, the last question. Suppose we have 3 RCDs in series, then how to do selectivity? Mr. Kamalesh, this RCD is our next webinar. Next Saturday, 11 o'clock is the subject. So we will discuss those in detail.
Can I just give a short answer to this?
Of course, yes.
So the ratio for selectivity is ×3. So if you have a 30 milliampere RCD, the one immediately upstream of it has to be 90 milliamp. So you don't get 90 milliamp RCD. Therefore, 100 milliamp RCDs are available. The further upstream of it then has to be ×3 of that. So 300 milliamperes. That is how you achieve RCDs in selectivity. It's a ratio of ×3.
Okay. All right. So it's a great experience and very good explanations. Krish, at the beginning, the speed was a little bit fast, but we have to reduce the speed probably in future. This is your webinar. Congratulations, and you did very well. Very good.
Thank you.
Extremely good. A lot of congratulations for you from the participants as well. Probably in the next webinar, which is on coming Saturday, 11 o'clock, we will be able to. The subject is earth fault protective devices. Means we will be talking more on RCDs and probably AFDD as well. So we will be able to make it much better. So thanks for all the participants. Over to you, Dominic, sir. You can conclude.
Yeah, thank you so much. Thank you, Krish and Mr. Gopakumar. There are few chat boxes I see. What will I get when I become a member? See, it is all what I give back to the nation rather than what I get from the nation. So, if you are electrical professions, there's a lot that you can give to the the nation. So, your knowledge, your experience, your network will be very useful to others. Okay, not that delivery, I would say. It's a huge network. When you see, look at our WhatsApp group of the members, which is around close to 600. There are very, very important discussions going on, clarifications, and best practices. What Mr. Gopakumar always says, 80% of our electrical contractor doesn't know what they're doing actually. So there are a lot of learning. As I said, there are accreditations happening, certification courses going to happen, and a lot of webinar and seminar. So for those who are member of NFE, they will get free access to all this and access to the website with knowledge section and the blog. All that will be available for the member. Today it's open. Later, as we progress, that will be available only for members. So there are a lot of benefit. You go to the website, you will get to know everything. I would once again urge all our participants here to become a member, because this nation has over 1 lakh, over 1 lakh maybe the electrical engineers. So we have only 600. We are only covered 0.9%. So a lot more to go. So unless you all come in, we can't make this nation electrically safe. That's the objective. So again, we look forward to see you again to Krish. I'm sure Krish will be enlightening us on the product that we want to discuss. So we'll continue this webinar series. I thank you for participating. Very encouraging. We are the only people who always get 500 plus registration every webinar. So which means everybody is quite interested in our topics. Look forward to see you. Have a great weekend with family and stay safe. Bye-bye. Thank you so much. Bye-bye.